So we added the pulsation loads on axis X and Y in the edit load cases table. So now we'll go to the analysis in the table of dynamic load cases. So in this case we need to create the dynamic loads, the pulsation load. So the wind according to X and Y is the have number 5 and 6. 5 and 6. Okay, so we go to the table of dynamic loads. We'll choose pulsation 21 position type. The load case number will be 567. The number of analyzed model shapes will be 15, and the corresponding static load will be 5. Parameters. Here will be 3.75 meters. Is it right? So really, I think we need to check this length and along the X and the Y direction. So now I will open the AutoCAD software and we'll check our size of metal tower. Just now I will write this 3.75, and then if it's not correct size, I will change it. Structure type first, reinforce steel, wind according to X. Okay. Next, the second load will be 8, pulsation 50, and here is 6. Along I-axis. Okay. Press OK button. Next time go to account of static load cases. Here I will create the load cases with all static loads. So our dynamic load has the number 7 and 8. I will start with the 7. Go to analyze, account cases. So I will write here 8. The first static load, then will be with the coefficient factor 0.95. I will add it. The second one will be with the conversion of coefficient factor 0.5. The third will be the same. The fourth will be the same 0.5, and fifth also the same, and the sixth also. So all of loads, despite the load own weight, will be with the coefficients 0.5, and then 5, 6, 7. I will check. So we need to add the number of the pulsation load, 8 and the 7. Okay, so now I need the 7. Nice. Add 7. 7, the first static load is for metal construction 0.95. For second 0.5. Third, fourth, fifth, and the sixth. Okay, press OK. Then we go to the design combination forces. Design combination forces, DCF. Here we should apply the loads. Ice load. For wind load, we will add the group of mutually exclusive load cases. 1, press apply. Next, also in the first group, and for pulsation will be the same group. Okay, press OK. Now we press the pack model. We'll save our model. And press the button Analyze. So here I want to check my where is it? I need to find it. Okay, no. Our tower. Where is our tower? Okay, I will go to the portal and I will find it in the site learning as the site. I will download. So I need to check the size of the tower in the bottom part. So let's see what we have. The first ultimate state, limit state. According to the first limit state, there are no problem with all constructive solutions. The second limit state also, so that there are very positive numbers, and we see that the serviceability also in a good positions. Here is for local backlink, no problems, and the cross sections is also applied very well. So all my sections that I applied for this tower works right without any problems. Now I'm going to analysis. I'm sorry, for results. In the displacement scale, I will decrease the size of the scale 5 times. It shows like a big problem with the tower, but it's not that. It's just millimeters, so less than 1 millimeter displacement from own weight. From the payload to 0.9, so 3 millimeters. From the snow, less than 1 millimeter. From ice load also. From load in X direction, not so big. From I direction, 9 millimeters. Pulsation according to X direction, not so big. Pulsation at Y direction, 8 millimeters. 8.64. So the biggest displacement is equal to 9 millimeters. That's not so big actual deflections. So now I will check the size of the tower. It should be 3000 750. If it will be more or less, it is 3,975. So here I need to write 9. So I change the size, the length, press OK, and again make the analysis of the tower. Okay, that's all. What will be next? So there are no foundation, as you see in our tower. So to make the right calculation, we need to correctly create calculation, we need the add foundations under our tower. So it will be basement for the tower. So what we need to do? First of all, I will save our model. Then I will go to the drawings. So on the drawing, I have the drawings for foundation. So I see that the depth of my foundation will be about 2 meters. So the column part of the foundation will have the size 600 millimeters to 600 millimeters, and the width of the lowest part of the column foundation will have the thickness 400 millimeters and the width 2,000 millimeters. Okay, so the length of the column will be 1,600 millimeters. So let's add it firstly. So what I need to do? First of all, I will make the copy of this node in the by the parameters in z direction minus 1.6 meter. Press OK. Then I will choose the rectangular bar 60 to 60 centimeters. We'll use element, add elements, and we'll add it. Then I will select it, make the fragmentation. I will select the lowest node and I will make the copy of this node to the main edge of the plate, basement plate. I will make copy by the parameters. My basement plate have parameters 2 meter to 2 meter. So I need to make the copy minus, according to x direction, minus 1, and according direction y minus 1. That is a needable point for the plate. Now I will first of all, I will choose the plate. Then I will go to the slab, creation the slab. And here I will write the size of my elements. It will be equal to half of meter for time, and again half of 1 meter for time. So my foundation is actually ready. That's column foundation. So now I will delete these nodes. So I will delete the stiffnesses, restraints. All restraints will be deleted. And I will delete, I will add the stiffness. I will add restraints at the edges of the plate. It will not move in the direction X and Y. So why I don't use the restraint for Z and other directions? Because there will be ground conditions under my foundation. So ground conditions we will apply some later. So now I will make the copy of it and then we'll add the ground conditions. First of all, I will add the additional characteristics for rectangular bar, reinforcement concrete column, concrete type, and reinforcement. Will apply it. Then I will choose the plate, so the basement. We'll use plate, slab, and the concrete with the reinforcement will be the same like rectangular part. Then I will select all of them, use the copy by the node, and we'll make the copy for 3 legs of the foundation. Then I will open the example of the report of the ground soil conditions. Just let me find it. Okay, it will be this. So this is a report about engineering geological conditions of soils in the object. Actually, it's not our project, but just some of them. So before starting design of and calculation of buildings and structures, we need to find the geological conditions, ground geological conditions of the building. So according to this table, we'll apply the characteristics for our soils. Let's open the position which I call it model of subgrade reaction C1 and C2, and we'll calculate C1 and C2. So vertical load will be, so actually this vertical load is calculated load. We need to take it from the calculation in the rigid conditions without foundation. So maybe on next lessons I will tell you about how we need to find it. Now maybe it will be enough to apply 10 tons for one column foundation. The depth of foundation 1.6. It's rectangular. The width of foundation 2 meter, and the ratio is 1. So 2 meter to 2 meter. Okay, geology. So there will be 3 layers in our soil. So the first layer will have a model of elasticity 22. So here we'll write 2,200 tons per square meter. The space and ratio 0.35. The depth of the layer. The depth of the layer will be here, so the client soils have the thicknesses from 3.9 to 6.5 meters. So I will choose the biggest one, 6.5. The depth of the layer 6.5. And here I see that the height is changed, 6.5. Then I will use density, 1.79 ton per cubic meter. 79. The stiffness coefficient will be permanent. So next layer, second layer, the ratio will be the same, the unit of weight will be the same, the stiffnesses will be the same, depths of the climb soil will be 1.4 meter. 1.4 meter. The ciliated model of elasticity is the same like it was in the previous one. So here I need to use this type of the soil. And the last one is the sand with the elasticity model 30, and here I will write 3000, ratio 0.35, the depth is 1.0 or 1.9, the weight, it's a density 1.96, 1400, it's a sand. Okay, so restrain maybe post okay, so maybe 50. Yes, so it was not so big load vertical for the such foundation with the such size, so it should be bigger. Maybe 50 will be enough. Let's okay, yes, 50 is enough, but 10 it's not enough. Yes, 50 tons, that's enough. Okay. We can apply it, or we need to choose the results method, the first or the second. I will choose the second. Apply. Now I need to assign elements. I will choose the bottom plates. Play add. Okay. And then I will write apply. Now I will use the information about nodes and will check. Does the play? It wasn't applied. We need to repeat this procedure again. Sometimes it happens that it does not apply it from the first time. Now I will check again, and we see that this C1 and C2 coefficient is applied. Okay. Restore models. Now we need to delete these three nodes, or these two nodes with a rigid connection. What else we need to do? We need add the restraints, like we did it in the cell beam calculation. Do you remember when we added the hingers for the constructions? So hingers is important part in all design. I will select the Sprengels. Select the Sprengels. Also diagonal bracings. No, it can be. It will. I will select them after I will finish with the Sprengels. I can check also this diagonal bracing elements. So that's all. Also these elements can be selected. Okay, these elements also can be selected. Okay. No, I will unselect these two ones. So then I go to the bars, hingers, and will apply the hingers for my positions. So on the scheme you see the added hingers. Now I will select this one and will add hingers on only in one part. I will select this leg and the opposite part. Now and it unselected. Again I will select it and apply this left part in the first name. Okay, next. This one. Okay. The same thing in the opposite two parts. first elements. Okay, that is good. That is very good. Now for these elements. For this. Okay. For this part, this. Okay. Oh, we write it here. It's not right. So maybe now some difficult to understand why I add the fingers in this positions and for not for all of them. So because we need to understand how they are connected, which is other. So which of them should have the node or which are not. Hmm? Okay. That's all right. Okay. That is very good. So it seems very good. Now I will add this nodes. Not this. Okay. So there was a little mistake. Change it. Right. So adding the fingers actually it's a long process, it's not a rapid process. That's why when you do it, you need really some time. Okay, so I will finish maybe by myself. Just I want to show you how it will go to the analysis. I will pack the model and make the analysis. So we added the ground conditions, we added the reinforcement, we added the concrete. Now there are not only the steel information about steel construction, but also information about reinforcement of our basement of foundation and the column part of it. So it also requires some reinforcement in legs. And what about results? How it work with the ground conditions from the own weight. Let's see. Okay, not so bad. The ground conditions is very good. You see that there are not. So the displacement is some increased, but not so many, just for 2 millimeters. So 2 millimeters actually it's not so big displacement for us. It means that our calculation, so there was some problem with my program. It means that our calculation is actually right. Oh, I think there are a big problem because I lost my ground conditions. I doesn't save it. That's very bad. But there are a video where you can find all information about how to do it. Okay?
Yes.
Don't forget save
Okay.
the model. Don't forget save the model, because every time there can be some problems with the soft LIRA SAPR 2017. Okay, thank you very much. If you have no questions, we'll be meet with you in our next lesson.